everyone. Welcome to the 15th session of Electromagnetic Theory and Interference course. In this session, let us learn about electric potential and we will see why electric potential is required, especially in electrostatics and the role of it. And we will see the potential due to a point charge and potential due to n number of charges. And also we will solve a problem based on this. So let us begin. So we already know that we are able to compute the electric field intensity due to a charge distribution from Coulomb's law. And when charge distribution is symmetric, we can go for Gauss's law. The third way of obtaining electric field intensity is from electric scalar potential V. So that is electric potential is denoted by letter V. From this, how we are going to get the electric field? That is the aim of this session. So this is a easier way because it is easy to handle the scalars. This electric potential is a scalar actually. So let us set a construct. Here there is a electric field is present and we are going to move a point charge from A to B in an electric field. So from the Coulomb's law, we know the force on a charge is nothing but Q into charge into electric field intensity. So work done in displacing a charge, okay, by the small amount dl is given by differential work is driven by force into distance. So F dot dl vector. And why here a negative sign? Because the work is done by the external agent. And if I substitute for F Q into electric field intensity, this dot dl remains same. And I am going to find the total amount of work done. That is equal to minus Q is constant. So I am going to integrate this E dot dl over the line A to B. So this quantity, okay, is called potential difference between the points A and B. VAB is the potential difference between the points. It is going to be the work done in moving a point charge. So work done divided by Q. If I do this in the above expression, I'll get minus integral over A to B E dot dl vector. So if you are interested in finding VAB, we know that A is the initial point, B is the final. And if it is negative, it is called a loss in potential energy. And it is if there is VAB is positive means there is a gain in potential energy. And one more thing, VAB is going to be independent of the path taken that we will see in the upcoming slides. And VAB, and we are going to measure the potential difference by joules per coulomb because it is going to be work done by charge, right? Or we can measure in volts also. So from this relation, we are going to apply the formula for electric field intensity due to a point charge Q divided by 4 pi epsilon naught R square into AR cap. If we apply, the DL now changes to DR into AR cap because it is along the AR vector only. So if I take the integral, the constant will be Q by 4 pi epsilon naught. Integral of minus 1 by R square is going to be 1 by R. So applying the limits, it is 1 by RB minus 1 by RA. So that is going to be just VB minus VA. Okay, VAB is VB minus VA. So these are the potentials at point B and A. Potential difference VAB, how can I consider it is potential at B reference to A. Okay, and in most of the problems where the point charges are involved, we are going to choose infinity as a reference. So we are going to take the infinity as reference. That is, we are going to move a point charge from infinity to a point R. So the potential at infinity is going to be 0. Okay, and if RA is infinity, what happens? 1 by RA is going to be 0. RB is going to be R. So the potential at any point due to a point charge is Q divided by 4 pi epsilon naught R. Yes. And if any other point is chosen as reference, instead of infinity, if we take any other point, we have to add the constant C here, right? Now we are going to if there is zero potential at infinity, the potential at a distance r from a point charge, how can we write as the integral form is the work done in moving a unit charge, okay, by the external agent to transfer the test charge from infinity to that point. So infinity to that point are how much amount of work done is done in moving a charge is going to be V is equal to minus integral infinity to r E dot dl. Okay, if the point charge is not located on the origin, it is not located at the origin but some other place, its position vector is r dash, but I am interested in finding the potential at r. So how will I find? It is nothing but q divided by 4 pi epsilon naught. Instead of r in the previous slide that we have written, we have to mention it r minus r dash vector potential at this. It's a vector form. Now, here we have considered only point charge. Now I can extend the idea to any charge distribution. So we are going to apply it for n number of point charges that are located at position vectors r1 vector, r2 and rn. The potential at r is going to be the same. Just I have to extend this q1 divided by 4 pi epsilon naught r minus r1 plus q2 divided by 4 pi epsilon naught into r minus r2 vector and its magnitude, etc. For nth charge also. What is constant out? 1 by 4 pi epsilon naught. What are the terms involved? So different charges are involved. So q1, q2, etc. q1. So qk summation k equal to 1 to n. And here r minus r dash is nothing but r minus rk. Okay, these for the n number of point charge distribution. Let us solve. Before solving a problem, let us see for the continuous charge distribution. For what we will do, we will just replace this summation by integral, and for total charge for different charge continuous charge distribution, we know that q is nothing but integral. If it is a line charge, we have to replace by integral over l rho l dl, like that we will write, no, rho l of r dash into dl dash divided by magnitude of r minus r dash vector. This is for line charge. Okay, why we are making it as r dash? Because these are the points where my uh, source is located. I told that instead of r, the source charge is located at this location, and r is a point where I need to find the potential, right? Similarly, I can write it for surface charge distribution, that is rho s ds over the surface integral I have to take. Similarly, I can do it for the volume integral, okay, volume charge density also, right? So generally, if you want to find the potential difference, it is going to be the potential at B minus potential at A, and that can I relate it to the line integral, negative of the line integral E dot dl, that is equal to work done in moving the charge, right? Now let us solve a problem. Here the two charges are given, located at vectors, position vectors r1 and r2. We are interested in finding the potential at this r vector, and we are going to assume that potential at infinity is 0. We already know from the previous that uh, because of the superposition theorem, we can write VR. If there are two charges, I can write q1 divided by 4 pi epsilon naught r minus r1 vector its magnitude plus q2 divided by 4 pi epsilon naught magnitude of r minus r2 vector plus I can write one constant. This constant is 0 because potential at infinity is 0. It's given in the question. So I want the q1, q2 is given. R vector and r1 vector is given. So just I have to find the magnitude. We already know how to find it. And after finding it, we are going to substitute here. Since both the charges are in microcoulomb, 10 power minus 6 I am taking, and this 1 by 4 pi epsilon naught, we already know it is approximately equal to 9 into 10 power 9 meter per farad. So I am substituting here. So if it cancel, I will get 9 into 10 power 3, and I am writing how this is a charge divided by its divided by its position vector magnitude, and here say. So if I find, I will simplify and get the answer in terms of kilovolt. Potential is measured at the particular point that is given in the question. I hope you understood how the electric